So in one-dimensional space, the Gaussian, it represents a probability distribution over line. So in 1D, the Gaussian represents the probability distribution, this x-axis, it are like the possible outcomes, and the y-axis, the curve, it is representing the probability distribution, like the probability of getting that outcome. And the Gaussian represents the probability distribution over a line. In 2D, the Gaussian, it forms an elliptical hill. So in two dimension, because we will be dealing with a surface, it will form a elliptical hill. And in 3D, the Gaussian, it becomes a soft volumetric blob, which is representing the spatial density. And this is basically a ellipsoid. So now it's very clear that 3D Gaussian is basically a 3D volumetric blob, which is representing the spatial density. So that's the 3D Gaussian. Now mathematically, like if we talk about general Gaussian formula for n dimensions, if we talk about the general Gaussian formula for n dimensions, we have this term, that is 1 upon 2 pi to the power of n by 2. This sigma is like the covariance matrix, so root of covariance matrix. So this term, it is representing the amplitude, and for 3D Gaussian, n will become 3. So this term will become 1 upon 2 pi to the power of 3 by 2, determinant of so under root of determinant of covariance matrix. Now let's try to feel this term. See, the idea is that if the determinant is having higher values, okay, so before understanding this formula, we will first understand how the covariance matrix looks like. Then this formula will be clear, because in order to understand this formula, these two terms we have to discuss. First this term, then this term. Like we will do the anatomy of it to get very clear understanding, like what is happening in this formula exactly, and why this formula is representing the spatial density. So before diving deep into this formula, let us first get an idea about the key parameters. So let us get an idea about the position, mean mu, that is the center position. So it is the center of the Gaussian blob. So center of the Gaussian blob is the mu. It's a position. And we also have covariance matrix. Now this is very important. Let us get a feel of it. So we already saw that covariance matrix, it represents the shape of the 3D Gaussian and also the orientation. Now how exactly the covariance matrix represents the shape and orientation is something which we should understand. So see, the idea is that the diagonal of this covariance matrix, it represents the variance. So this sigma xx, it is the variance along the x-axis, sigma yy is the variance along the y-axis, and sigma zz is the variance along the z-axis. So the diagonal, it is representing the variance, so the spread, and hence this diagonal, it is representing the shape. Because if sigma xx is like a higher value, it means that the 3D Gaussian, it is more spread across, like relative to the x-axis. Similarly, so that's the idea. So now it's very clear that the diagonal, it is representing the variance along the principal axis, like along the x-axis, y-axis, and z-axis. And if the value of, if we get a higher value of determinant, we will get higher value of determinant when diagonals will be of higher value. And if diagonals are of higher value, means we have lots of variance. It means the shape, it is more spread. The 3D Gaussian, it is not thin and sharp, rather it is more spread. And because of that, the amplitude of all the points has to be low. We will come to that very soon. But now it's very clear that covariance matrix, the diagonal, it represents the shape. And how it represents the shape? Because sigma xx, sigma y by sigma z z. It represents the variance along the x-axis, y-axis, and z-axis. More variance means it will cover more space, so the shape will be accordingly, it will be more spread. So that's the idea. Now, non-diagonal elements, it represents the correlation. Like sigma xy, it represents the correlation between x and y, and the value of it will tell the strength of the correlation, and the sign will tell, like if it is a positive sign, it means if x will increase, y will also increase, and if it is negative means if x will increase, y will decrease. So these non-diagonal elements, they are representing the correlation. All these, so this is like sigma xz, correlation between x and z. This is the correlation between y and x. This is a correlation between y and z. This is a correlation between z and x. Correlation between z and z. So that's the idea. So non-diagonal elements, it represents the correlation. And now definitely these values will also give us the orientation. Because see, the idea is that now, if like x and y are strongly correlated, it means that uh, like uh, x and y, they are dependent, and hence the 3D Gaussian, it will have an orientation accordingly. So the orientation, the angles which it is making, the 3D Gaussian along the principal axes, it will depend on these correlations. So if if there is a correlation between certain axes, that will basically tilt the 3D Gaussian accordingly. So these non-diagonal points, they represents the orientation. Now it's very clear that okay, if I want to represent a 3D Gaussian, what all information I should have, like the key parameters which I should make use of. So one is the center, that we call it the mu position. So that we call it the center of the Gaussian blob. We have to use that, and then we have to make use of something called as covariance matrix. Covariance matrix contains the information about the shape and orientation of the 3D Gaussian blob. And we also have opacity, which will give us the idea about the transparency and color. Now, with this understanding, we can decode the 3D Gaussian probability density function, or you can also call it like the spatial density function. So if we just focus on this, yeah. So see here, we can see that this covariance matrix, the determinant of covariance matrix, it is in the denominator. Because of that, what will happen is that when this value will be high, when the value of this determinant will be high, since it is in the denominator, the value of gx will be low. The value of gx will be low because it is in the denominator inverse relation. So when this determinant will increase, the gx will decrease. And this term is representing the amplitude. Now it's very clear that we already saw, we got an idea that if the determinant of covariance matrix is high, it means diagonals are having higher values. Higher value of diagonals means the 3D Gaussian is spread. And if it is spread, to balance the energy, the density of the points has to be low. Because see, if the variance is less, if the 3D Gaussian is thin and sharp, then the density has to be high. Like all the coordinates, its density, its amplitude will be very high. And if the variance is high, so now this uh, formula is giving us an idea that how it works. So this term, it is representing the amplitude, because what this formula is telling us that okay, in the 3D Gaussian space, let us take any random point x. Now this point x, it will have three coordinates x, y, and z. Now for this point, what will be the amplitude? It will be given by this 1 upon 2 pi to the power of 3 by 2, like root of determinant of covariance. So the intensity this amplitude is taken care by this. Now the other term, if we try to decode that, this exponent term, so here it is e to the power of minus 1 by 2 x minus mu whole transpose, like x minus mu in bracket and then transpose multiplied by inverse of covariance matrix multiplied by x minus mu. Now see, x is the point which we are interested in, any random point. Mu is the center. So x minus mu is like the distance of the point from the center. And that is very important because see, probability density, it will depend on the distance of the point from the center. Because we know that as we, in the center, the probability has to be high, the probability density has to be high, and as we move away from the center and we as we keep on moving, because after a point of time it will start getting blurred, because the 3D ellipse, the 3D Gaussian, since it is elliptical, after a distance it will start vanishing, so the probability will start decreasing. So x minus mu is a very important term, and now it is making sense, because the probability density of a point will depend on its distance from the center. So that is what is taken care by x minus mu. So we are calculating the x minus mu, that is the distance of the coordinate from the center of the 3D Gaussian. We are doing the transpose of it, and then we are multiplying it with something that is inverse of covariance. Now see, inverse of covariance matrix gives us the precision. Inverse of covariance matrix gives us the precision matrix, because covariance matrix, it contains information about the shape and orientation, and the inverse of that matrix contains the information about the precision. We also call it the precision matrix. Now this term precision, it is containing information about the shape and orientation, and that is very important in determining the probability of a point, because we have to have this information. Because once we know that, okay, what is the shape of the Gaussian, 3D Gaussian, if it is more thin and sharp, uh, after a certain distance, the probability should vanish. And if it is like fat, spread, then for long distances also it will have certain probability of, like certain possibilities are there that point will exist. So this precision matrix, sigma inverse, it is also playing a role. Now the idea is this, see here minus is there. So the idea is that if this term will increase, if this term will increase, the probability density will decrease, because it will be in denominator, because it will be in denominator. G of x will decrease. And when it will increase, let us understand. See, this will increase when the points will be closer to the center. See, as point will, okay, so see, this will increase when point will be far away from the center. Because see, if the point is getting away from the center, this difference will increase. And this difference will increase means this exponent will increase. Because this minus we are ignoring now. Why we can ignore it? Because we are already taking it in the denominator. So in the denominator, this minus will not be there. So the idea is very clear that, okay, if we keep on moving away from the center, if the value of, because mu is fixed, if x is increasing, it is moving away from the center, it means this distance will increase. So x minus mu will increase, then this entire term will increase. And now it's very clear that if we are moving away from the center, the probability has to decrease. And that is what is happening. G of x will decrease. And similarly, if we talk about this inverse of covariance matrix, we already saw that covariance matrix, higher value of the determinant of it means that it is spread. That the shape is like spread. Now inverse means inverse relation. So the idea is that when the 3D Gaussian, it is thin and sharp. When it is thin and sharp, then sigma inverse will have a higher value because of the inverse relation. because here we are taking, so that is about precision matrix. So that's why we call it sigma inverse as precision matrix. The higher the value of sigma inverse, it means the 3D Gaussian, it is precise, like it is thin and sharp. And when the 3D Gaussian it is thin and sharp, then what will happen is that if x starts drifting away from the center, the probability will start falling significantly. See, it's very easy to understand. I'll tell you how. Let us suppose I have a thin and sharp 3D Gaussian and I have something like a spread 3D Gaussian. Now I can make it a bit long, like it is thin and sharp. Now see what will happen is here, like, like let us suppose this is the center. After a point of time, like let us suppose the point is here. So here the probability will become very close to zero. It will not be zero, like, but it will be like 0.000001, something like that. It will be very close to zero. And similarly, let us suppose the same center and the same distance. But because of the shape of the 3D, this 3D Gaussian, this probability for this point is not zero. It cannot be zero. It has to be a significant number. And that is what is been decided by this sigma inverse. Because for this 3D Gaussian, the value of sigma inverse will be very high. Because here it is thin and sharp. It is precise. But for this 3D Gaussian, since there is a lot of variance is there, sigma inverse value will be very low. And when sigma value will be low, this exponent will decrease. And if this exponent will decrease, g of x will increase. And that is what we want na probability density. So we got a intuition of this formula, like the probability density function, we call it. Now, what is the importance of it? So see, we already saw that, in the previous module, we saw that we can represent a 3D scene either in the form of geometries or implicitly using mathematical functions. Implicitly using mathematical functions. Now, one of the ways is the neural radiance field, wherein we can train a neural network and that neural network will represent a mathematical function. That is one way. Wherein we don't know the mathematical function, we train a neural network and neural network will derive a mathematical function. So that the trained neural network is representing a mathematical function. That is one way. Another way we saw is the 3D Gaussian. We can represent a 3D scene using 3D Gaussian. Now, so for that also, we will be making use of a mathematical function, and this is the mathematical function for that. So in order to represent a scene using 3D Gaussian, we have to make use of millions of 3D Gaussian, wherein every 3D Gaussian will be defined by this probability density function, which will govern the density of the points across the 3D Gaussian, and it will depend on the center of the 3D Gaussian and the covariance. And along with that, two more parameters we will make use of in order to define 3D Gaussian, that is the opacity and the color. So now we got a very good understanding that how we can represent a 3D Gaussian mathematically. So this formula, so here n we have to replace it by 3. So this formula is basically the mathematical representation of a 3D Gaussian, wherein this formula is telling us that, okay, if this is the point x, and point x means it will have 3 coordinates, x, y, z. So if this is the point in space, so what will be the density of that point? Or what will be the probability density of that point? So in this way, with this formula, if we fix the center of a 3D Gaussian, and with the covariance which is containing the shape and orientation, so with the center position covariance matrix and this formula, we can generate a 3D Gaussian, or we can represent a 3D Gaussian. And like when we will be representing the scene, we will be having millions of 3D Gaussian, and every 3D Gaussian will be making use of the same formula, but the parameters will be different. The center will be different, the covariance will be different, the shape and the orientation of all the Gaussians will be different, the color and the opacity. So this is the mathematical representation. So we can think each Gaussian as a fuzzy ellipsoid floating in 3D space that contributes light and color to an image. So this is like a very good intuition wherein 3D Gaussian, you can imagine it to be something which is floating in a 3D space, and we will have millions of it. Every 3D Gaussian will contribute light and color to an image, and we will blend those millions of Gaussians to generate an image. And that is what is 3D Gaussian splatting is all about.